said. So we're flipping a fair coin, or 10 fair coins. So we have these 10 fair coins, coin number 1, coin number 2, all the way up to coin number 10. And each coin can be heads or tails. And we're interested in events that are built out of these things. And the first question says, all outcomes are equally likely, so the probability of getting 5 heads and 5 tails is the same as the probability of getting 4 heads and 4 tails. Let's see what people thought about this one. So we know about outcomes. This is something we talked about before. And let's see what people said. Aha, pretty split, 20 to 36. So kind of a medium-ish majority on false there. All right, what about this one? All outcomes are equally likely, so the probability of getting heads, 10 heads in a row is the same as the probability of getting this sequence. I actually flipped some coins. Okay, I didn't flip real coins. I flipped some digital coins. That's how I made this sequence. I ran a little simulation that said, please flip 10 computer coins for me, and it came out with tails, tails, heads, tails, heads, tails. Wait, I lost track now. Tails, tails, heads, tails, heads, tails, heads, heads, tails, tails. Very nice looking sequence. Which one is more likely? Is it this one or this one? What did people say? All right, this one, 39 people said true, and 17 people said false. The probability is the same. People said true. This one, I think, is quite counterintuitive. Because, you see, heads, 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 heads seems like a really special sequence, and this seems like some super generic sequence. And you might think, oh, a special sequence like that should be way, way, way less likely than some generic-looking sequence like that. So you might think they're different, but I have not stumped most of you because the correct answer is true, and you got it right, or most people did. The reason this is sort of counterintuitive is sometimes people think of this kind of sequence. They don't imagine this sequence exactly. They imagine sequences that, quote, look like this sequence. So you might imagine shuffling some of the heads and tails here. You get a sequence that kind of feels the same, whereas this one, this is the only one that has all 10 heads. So this one is sort of unique in a way, whereas this one, there are many other sequences that, quote, look like it. And if you say, what's the probability of getting this sequence or one that looks like this one, then of course the one that looks like this one is much more likely because there's many sequences that, quote, look like this one. And actually in part 1, this is exactly the reason why the answer to this question is false, which again, a medium-ish majority of you got. There are more sequences that have 5 heads and 5 tails than there are sequences that have 4 heads and 6 tails. So even though every individual sequence is equally likely, as we saw down here, the 5 heads, 5 tails is more likely than 4 heads, 6 tails, just because there's more ways to do it. There's more ways to do it. I drew a little graph here, a little calculator in my favorite graphing calculator program, Desmos. Let me see if I can make it a little bit bigger. Okay, there we go. So I have this nice little bar chart. I can even maybe zoom in a little bit. Let's go all the way up to y equals 0.4, say, to make it a little bit bigger. This is the probability distribution function, or the probability mass function that we saw last class. And remember, it's a function where the input is the lowercase x, is the non-random thing you are looking at, and you're asking what is the probability that the random variable equals x. And in this case, the random variable I'm talking about is the number of heads in 10 coin flips. And so if you want to do 5 heads versus 5 tails, this is x equals 5, and this one is x equals 4. So if we compare x equals 5 to x equals 4, we see that the middle one, where x equals 5, has a probability of happening of 0.246, so 24.6% chance to get 5 heads. And 4 heads is only 0.2, 20.5%. The fun thing about this calculator is you can change some little parameters in it. I have this thing called p and n. We don't know what p and n are, but the fun thing that we're going to learn after today's lesson is what they mean and what this distribution is and where it comes from. And then once we know that, we can do the fun thing of animating it. So in Desmos, you can animate this thing, and it does the wave. So the probability distribution function can be skewed to one side or the other side, depending on how you change these parameters, depending on what you do with the coins. And then the other thing you can do is you can add more coins. So this was 10 coins, but we can go all the way up to 100 coins. We can add more and more coins here, which is the fun thing we're going to do. And we're going to get this cool-looking wave. This is an important part of statistics. This little wave picture is sort of the basis of a lot of modern statistics. Okay, that's a little preview of what we're going to do. Any questions or comments while the thing waves around on the screen? Okay, yeah. This problem, yeah. Yes, okay, so the thing that is different between question 1 and question 2 is in question 2, I'm giving you a specific sequence. So I'm comparing two specific sequences. But in question 1, I have grouped together many specific sequences into one bundle, right? 5 heads and 5 tails. Is there one specific sequence that goes with 5 heads and 5 tails? No, there's not. There's actually many, many sequences that have 5 heads and 5 tails. You could have 5 heads at the beginning, 5 tails at the end. You could have alternate tails, head, tails, 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 tails. There's lots of them. In fact, we're going to count exactly how many momentarily. And so the reason that number 1 is false and number 2 is true is that in number 1, we're comparing two differently sized groups. And in number 2, we're comparing two groups that are both size 1. So it really comes down to you need to know which outcomes are equally likely. The outcomes that are equally likely are individual sequences of coin flips, not groups of coin flips. That's right, yeah. Every individual sequence is the same. It's just that this 5 heads, 5 tails has the most sequences. Great, this is a really common misconception. And I think it's one of those things where if you don't think about it, you'll be confused. Like you have to sort of, everybody has to sit down and be like, what the hell's going on here, and think about it at least once before it sort of makes intuitive sense. But most people got it right, which is impressive. Any other questions or comments? Okay, so let's learn about this thing. This thing is called a binomial. We're going to lead into this momentarily. We have some nice slides here on the PowerPoint that will tell us about the binomial. Let's go into this. More earn stuff.
Okay, so the pre-post, this was the last of the pre-post of last day. I did not put a pre-post today for a good reason. I don't want you kind of looking ahead at too much. What we want to do is actually think of the derivations here. And we're going to derive a couple special probability distributions, the binomial distribution, and eventually we'll get to the geometric distribution. And the reason I like these derivations is they require rules, what we've learned about probability and counting from earlier this semester. We combine them together and we create these equations that look kind of complicated, somewhat complicated, and yet they're very easy to derive from first principles when you really kind of think about what's going on. So here's one example here. Consider an earn example. And you've got k red balls and n minus k balls, which are white. And we'll consider a couple of probability experiments where we randomly sample with replacement. Okay, so why with replacement? Well, the key idea is going to be that each time we reach into the urn and grab a ball, the probability of getting a red will always be the same. The probability of getting a white will always be the same. Of course, the probability of getting a red or the probability of getting a white is simply dependent on how many balls are in the urn, how many of those are red, how many of them are white. Okay, so we actually don't really need to know the values of n and k. All we need to know is the probability of getting, for example, a red ball, and whatever that probability of getting the red ball is, 1 minus that probability will give us the probability of getting a white ball. Okay, so we can now simplify this to, let's not really worry about how many balls are in the urn. Let's not really worry about how many are red and how many are white. Simply, what is the probability of getting any particular color on any particular draw? Okay, so we're going to do these derivations on paper, and the reason we're doing them on paper, you see, that slide indicates paper, I think sometimes it's just easier to get things locked into your brain if you worked it out yourself and kind of think it through. And scratching things out on paper is often a very good way to get things together. Now, well, that's the paper. I'm going to jump ahead for a moment, and then I'm going to come back. I'm going to come back to the paper. And I'm going to show you a messy slide. This will come up in the post after class. So I just want to let you know where we're going to get to. Okay? So we're going to come up with the derivation of this particular equation right here, the binomial distribution. It's probability mass function. And it looks kind of funky. Okay? Kind of funky.
You're not going to believe this. This is the same formula that I did this morning.
It is
Can-
the
can
same
you believe
formula.
that?
It is
Let's
the
see.
same
Let's
formula.
let's see if we can find where the formula is in the computer. There's lots of silly stuff over here. Ah, okay. Look at this. And we got this b. This b. What is b? B. Okay. So look, I put in this little funny ratio of factorials. That's the same as your n choose x. I called it n0. This is n0 choose x, and then I got a p to the x, and then a 1 minus p to the n minus x. So it's exactly the same as yours. Oh, what is q in yours?
What is Q? Okay, well, let's kind of just take a look a little
right, we're
bit
gonna
at the
find out
definitions.
What q is?
Okay, so first of all, what is our random variable itself? Well, we're going to count the number of successes, and we have to define what is a success. Well, it's simply what you decide to call a success. So we have red balls and we have white balls, and we will pick one of them and call them the successes. So for example, if we are counting the number of red balls we get in our n trials, and it's the number of trials we're going to make, that's the number of pulls from the urn with replacement, then getting a red ball is a success. And if I wanted to count the number of white balls instead, well, then that would be a success. But if I call the red balls a success, getting a white is a failure. Okay? The definition of success or failure is simply based on what are you counting. In real life, sometimes a success is something really nasty, like having a terminal disease. Okay? Nobody would call that a success, except that if that's the thing we count, then that is the success in the terms of a binomial distribution, or whatever distribution we're working with there, okay? And so the thing to emphasize is that the trials are independent of one another. Again, we are sampling with replacement here. If we sampled without replacement, that would not be necessarily the case. And the probability of a success on each trial is a constant p. So the idea is that the probability of a success stays the same on every trial. Doing this with the urns with replacement, that's not a problem. In some real life situations, that may not be always exactly accurate. So this is just reiterating, there's two possible outcomes, and that's why we call it a binomial distribution. There's two names to the outcomes. And one we'll just call one, the one we count a success, and the one we don't count, well, the one that automatically is counted as, if you flip a coin 10 times, if you get 4 heads, well, you automatically know you got 6 tails, for example. So the Q, I like defining the Q as the probability of a failure. A lot of books don't bother defining a Q. They just do 1 minus P in there, and I just think it simplifies the notation in our equations a little bit. If we just say, okay, we'll define Q as 1 minus P, the probability of a failure. And we have in this distribution then something called 2 parameters. So the idea of a parameter is a very important concept of statistics. It's something that often takes a very long time to wrap around your head to exactly what a parameter is, okay? So we'll just try to get you focused on that idea right now. The idea is that these 2 quantities, the n and the p, they will define the probability distribution for any type of situation where these conditions of independence between trials and constant probability of success on each trial holds, okay? And so they will generate the same probabilities each time for any, as long as the n values and the p values are the same. So these parameters, n being the number of trials, p being the probability of a success on each trial, that will define a binomial distribution under any circumstances, you know, whether it's urns or flipping coins or all kinds of other possibilities there. And again, we emphasize that this is a trials are independent, so this is what we call a sampling with replacement distribution. Now, if we sample without replacement, well, we know the probabilities will change from trial to trial. Under some situations, we might actually sample without replacement, and we find the binomial distribution is a adequate approximation. So that's sort of something to come. Now, where are we next? Okay, well, I don't want to go there. I want to go back. I want to go back to my paper. Okay, so my paper. Oops. That one has to go in the garbage. I'll just call it deriving a binomial, the binomial distribution. We can, well, we could come up with another title which might be slightly more accurate, but this is adequate for our purposes. So consider a sequence of n trials where we obtain x successes which I'll denote with an S, and therefore n minus x failures. And we'll denote those with an F, okay? And again, just going through, we did say n equals the number of trials. And P is going to be the probability of a success on any trial, any particular trial. And Q is going to be the probability of a failure on any trial. And of course, Q is just equal to 1 minus P. Okay, so we can consider any sequence. Now, it doesn't matter which sequence we pick, but let's just start off with a simple sequence that we can see, and then we
I have a good one. Can we do this one? The one I did this morning. Let's do this one. This is my new favorite sequence.
Your new favorite sequence.
Oh, wait a second. This says T and H. Yours say S and F.
Okay, well, we will translate yours.
We're going to translate. Okay. Well, we got to decide which one's the success and which one's the failure.
Let's use...
It depends if you're for or against the monarchy.
Mihai's sequence.
I have to decide now if I'm for or against the monarchy. This is a lot of pressure.
It's a lot.
We're being recorded, so I might get executed later. I think I'm for. Wait, hold on. I could get executed either way.
Okay.
I don't know.
You can pick whatever you want.
Let's be for the monarchy today.
Okay.
So we'll say heads is a success.
Okay. Oop. Heads equals a success, which is an S, and tails is going to be a failure. That's an F. Okay. So his sequence is, just tell me that sequence again there.
Tails, tails, heads.
Tails, tails, heads.
Tails, heads.
Tails, heads.
Tails, heads again.
Tails, heads again.
Heads, tails, tails.
Heads, tails, tails.
Yes.
Okay.
Very beautiful, random-looking sequence.
And so I'm going to translate that. That's a failure, a success, a failure, a success, a failure, a success, a failure, a failure. Okay. We've got that. Now we got 1, 2, 3, 4, 5, 6. 6 failures and 4 successes. Okay. So what is the probability of this sequence? Well, if it was a fair coin, the probability of a head and the probability of a tail would be the same, but let's generalize that we don't necessarily have to have the same probability of a success and probability of a head. And so we're just going to put it in terms of P's and Q's, okay? It could have been an unbalanced coin, for example. So let's just do that one. The probability of a failure is Q times the probability of another failure is Q. Again, we've got independence here. Times the probability of a success is times P times, oops, we've got a failure, times a success, times a failure, times 2 successes, times 2 failures is 2 Qs. And what we end up with is we ended up with P to the 4th, Q to the 6th, or, well, we could generalize that. Or in general, for K successes and N minus K failures, we would end up with the probability of a particular sequence oh, come on, have room on my page, is, too limited. So we'll have to slip to the next page, which is okay. Is P to the K, Q to the N minus K. Okay? So in this particular example, Professor Nika flipped the coin 10 times. Our N was 10, and the number of successes counted was 4. That's our K, and therefore the number of failures was N minus K. 10 minus 4 is 6. Okay, so this is just a somewhat more general possibility. Now, next question. That's just the probability of a particular sequence. But For example, to get 4 heads and 6 tails, was that the only way to get 4 heads and 6 tails? No, there's a bunch of other ways to get 4 heads and 6 tails. And in the mathematized question, of course, when the comparison was against 10 heads versus this sequence with 4 heads and 6 tails, again, many of you might have thought, well, of course, I could switch those around in different orders, but in fact, we're talking about that one particular sequence. But if we simply asked you the question of getting, what was the probability of getting 4 heads and 6 tails, where we didn't care about the ordering of the heads and tails, we've got to be able to count all of those, okay? So, so I'll put it this way, but how many ways are there of getting k successes and therefore n minus k failures? We could look at this in the specific example. I'm going to do the general. We'll just double check it with the sequence of 10 trials, but let's just kind of think about this particular sequence. Well, this is equivalent to asking how many distinct ways are there of ordering n objects when there are k of one kind and n minus cut k of another kind. So the one of one kind are not actually distinguishable, but again, we can think of them being distinguishable just like when we're permuting the letters of pepper. We can think of a P1, P2, P3, but we also recognize when you flip, for example, 2 P's, that doesn't change the sequence of letters that you've got there. So, all right. So our answer on that one from our counting rules is, depending on how we like to think it through, I typically would go with there are n factorial ways if they were all different. But the one kind, the k of the one kind are not all different. And so what I think of is that I would divide out by the number of ways of permuting the k of the one kind, the ways of arranging that we would have arranged those as if they were distinct, but they're not distinct. And so that accounts for the different arrangements of things that I can kind of say, how many ways would I have arranged them if they were distinct, but they're not. And I also have the n minus k of the other kind. And again, I say if they were all distinct, but they're not. So I'll divide out by that. And that actually just comes out to the formula for combinations. which is and choose k. Okay? Let's test this. Okay, so 10 choose 4 is 10 factorial over 4 factorial, 6 factorial, and then we can work that out. I mean, well, I'm a simple man. I need simple solutions. Times 8, 10 times 9 times 8 times 7 times 6 factorial over 4 times 3 times 2 times 1, but let's put it in just to be full, times 6 factorial. So when you cancel out in factorials, you got to be a little careful. You got to, factorials like 6 factorial and 6 factorial will cancel out. And let's see, what else are we left with? Well, 4 times 2 will take that one out, and that will take that one out. Sorry, 3 times, not 1 time. What have I got? 30 times 7, 210 ways. Does that match up with your count?
Well, I had the computer do it, so I don't know.
210 ways. Just got to be 210 ways. So almost everybody's calculator also has a combination key. You can actually check 10C4, 210. Did I work that out right? Anybody see a problem? 210? Got it? Got it? Okay. So it was 210. So again, thinking back to that mathematized question early on, you know, if you saw that particular sequence and you were just automatically thinking, oh, but that's not the only way of getting that number of heads and tails, you were absolutely correct. There were 210 ways of actually ordering the heads and tails such that they were distinct sequences. But that wasn't the question in the
That's why this one is counterintuitive, right? This one feels a lot rarer because there's only one sequence of all heads, but there's 210 sequences that, quote, look like this one that are just, there's 210 different ways you can shuffle these up and still have 4 heads and 6 tails. So when you see this kind of intuitively, your brain is like, oh, this is like some sequence over here. There's a lot like that one. And so you kind of intuitively think that this should be more likely than this, even though the individual sequences are equally likely. It's just that there are way more ways you can have 4 heads and 6 tails than you can have 10 heads and 0 tails, that was part 1, right? 4 heads and 6 tails versus, well, we did versus 5 heads and 5 tails, which would be a little bit more. Should we work out what is, how many ways would there be for 10 heads, 5 heads and 5 tails? I guess that would be 10 choose 5.
Okay. And
oh, I guess we have to check, right? Maybe I made a mistake in the mathematize.
so let's also just check out n equals 10, k equals 5. 10 choose 5 equals 10 factorial over 5 factorial, 5 factorial. And I go 10 times 9 times 8 times 7 times 6 times 5 factorial over 5 times 4 times 3 times 2. I usually leave out the 1, but I'll put it in here, times 1 times 5 factorial. The 5 factorials go bye-bye. The 4 times 2 takes out the 8. The 5, it's going to leave 2 up on the numerator, and that's going to, that 3 is going to take out, divide out through the 9 times 3. And, oh my God, now I've got such a big number to work out.
252? Yeah. Everyone else?
252? 252.
So there are more ways. There's a slightly more. Before there were So yeah, the mathematize that we said this morning, we kind of did it intuitively, but now we have the calculation. There's 252 ways you can have 5 heads and 5 tails, but only 210 ways you can have 4 heads and 6 tails. And that's why 5 heads and 5 tails is more likely than 4 heads and 6 tails. There's just more ways. There's simply more ways.
Couple additional little observations. One is that n choose k is also equal to n choose n minus k. Other words, the number of ways of arranging k successes and n minus k failures, if you were to flip your successes and failures, you're going to come up with the same number of ways of arranging them, okay? And you can verify that for yourself, kind of easy. And then one of the odd ones is what happens when you do n choose n. In other words, k is actually equal to n. And you get n factorial over n factorial divided by n minus n factorial.
Oh,
now,
no,
what is that little beast?
You can't divide by 0. This is a disaster.
It is a disaster. We can't divide by 0.
Wait. Oh, okay. That's lucky. Seems made up.
Pardon?
Sounds made up.
It sounds made up.
This is why, I don't know if you remember, when we did the combinations a long time ago, we didn't do it with dividing by n minus k factorial. We did it by counting down, you see?
Yeah.
And that way you avoid this problem.
But it's a good question.
Yeah. It's the number of ways you have 0 things. How many ways can you put the 0 things in order?
Only one way.
One way. You just do it. That's the one way.
Right.
Yes. I remember when someone told me this, I was like, you're lying. You made that up. But I guess everyone does that. That's the right answer. So.
It's what everybody does.
Okay.
So, yep, everybody does that. So just by definition, 0 factorial is 1.
The final answer, n choose n equals 1, that one makes sense. That's because that's asking how many ways can you make a sequence of length 10 with 10 heads. And there is one way to make a sequence of 10 heads or tails with 10 heads, which is there's the only one way is heads, 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 heads. That's the only way. So the final answer is good.
Final answer is
and
good.
That's another way you can justify why 0 factorial equals 1.
Okay.
Yeah. All right. That's silly. Okay.
So let's put our two pieces together. To arrive at the, I'm going to call it the probability mass function, the PMF. I'll define it again here because we're just getting used to this. For a binomial random variable x. So our pieces, let's put our pieces, I'm going to put my pieces on another piece of paper because I want to be able to write things underneath it. If you are right at the bottom of your page right now, I suggest like putting it on the top of another page so that you got some room to put things underneath. So I'm going to take those two pieces And I'm going to start off near the end. I had this p to the k, q to the n minus k. And then I had to figure out how many different ways they went together. And each of those sequences are going to have the same probability. Okay? So maybe I should have wrote that somewhere. So maybe I'll come back to this. But I'm going to put in my number of sequences, number of ways of getting k successes and n minus k failures. So this is going to be n choose k. That comes out the front. And what that is giving me is the probability that x takes on the value of x, which we'll call little p of x, is equal to n choose k, p to the k, q to the n minus k. But,
I think there's a mistake.
Oh, you could be right.
Well, the first thing, you forgot the line in the probability, which everyone, my favorite.
You're absolutely
my favorite
right.
P operator.
You're
So I like to do a script P, because otherwise I'm on my page and I'm like, P, P, P. Oh, there's too many P's, I get confused. So I like to put a line here. If you don't like to do it, that's fine. That one's optional. But there is another mistake.
There is another mistake.
anyone
My
see-
x and my k. My x and my k.
Well, you gave it away. All right.
I gave it away. Yes. Okay. So if I'd said the probability x equals the little value k, I would have done p of k equals n choose k, p to the k, q to the n minus x. Or if I use a little x, well, that p of x, and choose x, p to the x, q to the n minus x for, well, is it for all values of x? Well, we know that the x can't be greater than n. We can't get an x of 3.5 or something like that. So we need to specify what values of x this works for. And could x equal 0? X could, right? If we're counting the number of heads, it's possible we get all tails. So x equals 0, 1, 2, and so on up to n. And just to be complete, we'll say 0. Okay, let's just do it here. 0 otherwise. Okay, so we've created our function there. And let's just go on the screen for a second. Let's go on there. We have done this, except my slide, you see, is well, that's generally what we'll say for the probability mass function, but what's left off of that is the little additional part of 0 otherwise. Okay, so it's important to recognize that there is a 0 otherwise that goes with that that equation. Now, well, we're going to have to leave this for the next day.
Well, what we do, we have mine. You see, I made one already.
You already made one.
Well, I have this the thing I showed at the beginning of class. So this is plotting exactly the function that we just derived. So you get to choose n and p. Those are your parameters. And then the graphing calculator draws the whole little distribution for you. So I guess we did the example with 10 and 0.5. This was our starting mathematized example. And it turns out with 10 and 5, 5 is the most likely. So you start at 0. 0 is very unlikely. Then 1 head, 2, 3, 4, 5. 5 is the most likely. What happens if we change it to 0.6? which one is the most likely if we make it 0.6? Well, we got to count it up. Okay, this is 0, x equals 0, x equals 1, 2, 3, 4, 5, 6. Now x equals 6 is most likely. So it turns out that the most likely one is somehow related to the p-value and the n-value. It is the product. Well, let's try 0.7. Make sure I'm not seeing ghosts. 0.7. Okay, there we go, 7. What about 0.8? What if I make it something in between? What if I do 0.75? That's interesting. Ooh, okay, if we make it 0.75, we make it a little bit less. Oh, we can kind of make them equal. So and now 7 and 8 are sort of equally likely. I guess 8 is just a smidge more likely. So it's kind of this like this curve that grows and it kind of reaches a maximum at the product of n and p. If you watch the video, you might remember that n and p multiplied together are something important related to this random variable. We're going to talk more about this in future classes.
On Monday.
Yeah, any last minute questions or comments? All right, we'll see everyone on Monday. Have a fantastic weekend.